Welcome. Today we study one of the most elegant objects in approximation theory, the Bernstein polynomials. Our journey runs from a pure existence theorem of Weierstrass in 1885 through Bernstein's constructive probabilistic proof of 1912, all the way to the Bézier curves that power modern computer graphics and computer-aided design. The thesis of this lecture is simple. One formula ties together probability, approximation theory, and geometric design.
Here is our plan. We begin with motivation and a little history. Then we build the mathematical foundations we will need: binomial coefficients, the binomial theorem, polynomial spaces, continuity, and uniform convergence. After that, we define the Bernstein basis and the Bernstein operator, prove convergence, work through 4 examples, look at many pictures, and finish with Bézier curves, structural properties, applications, and a summary.
Approximation theory answers a very practical question. A function we care about may be expensive, awkward, or known only through data. Can we replace it by something simple and control the error we make? Polynomials are the canonical simple functions. You only need addition and multiplication to evaluate them. They differentiate and integrate in closed form, and finitely, many coefficients describe them exactly. The foundational result is the Weierstrass approximation theorem of 1885. Every continuous function on a closed interval can be approximated uniformly by polynomials. That means the maximum error over the whole interval can be made as small as we like.
But there is a catch. The classical proofs are pure existence arguments. They guarantee that a good polynomial exists, yet they never tell you how to write it down. Bernstein's contribution in 1912 was to give an explicit, universal formula and, as a bonus, a probabilistic proof.
Let me stress the gap that Bernstein closed. Earlier proofs said, a good polynomial exists. Bernstein said, here it is. His idea is disarmingly simple. Sample the function on the uniform grid of points k over n, and weight those samples by binomial probabilities. The resulting polynomial converges to the target for every continuous function, and the proof uses nothing more than the law of large numbers. The same construction would, decades later, become the algebraic heart of Bézier curves.
Before the technical work, here is why it is worth your time. In pure mathematics, the construction gives a constructive Weierstrass theorem and the prototype of a positive linear operator. In numerical analysis, it gives stable, shape-preserving approximation. In geometry and graphics, it is the Bézier curve, used in computer-aided design, fonts, and animation. And in data science, it appears in smoothing, monotone regression, and the approximation theory behind neural networks. One formula with a remarkably wide reach. A word about the man. Sergei Bernstein was a Russian and Soviet mathematician, born in Odessa in 1880. He studied in Paris and in Göttingen. In his 1904 Paris doctorate, he solved Hilbert's 19th problem on the analyticity of solutions of elliptic partial differential equations. That was already a major result, before the work we study today. He later founded an influential school of analysis in Kharkiv and contributed deeply to the foundations of probability. This timeline shows how Bernstein's career threads through 3 fields. He was born in 1880. The Paris doctorate and Hilbert's 19th problem came in 1904. The Bernstein polynomials arrived in 1912, the green peak on our timeline. Then came the Kharkiv school in the 1920s, foundational probability work in the 1930s, and a long legacy through the Academy of Sciences until his death in 1968. That single 1912 paper is the bridge between probability, approximation theory, and, eventually, computer-aided geometric design. A few facts worth remembering. Bernstein's 1912 convergence proof is essentially the weak law of large numbers in disguise. We will see exactly how. His name is attached to several results. The Bernstein inequality, which bounds a polynomial's derivative by its size, Bernstein's theorem on completely monotone functions, and the Bernstein-von Mises theorem in statistics. And the basis he introduced for an abstract approximation theorem became, around 1960, the practical tool that car designers at Renault and Citroën used to describe smooth body panels.
Let us assemble our tools. The binomial coefficient, written in choose k, counts the number of ways to choose k objects out of n. We will use 3 facts: its symmetry, n choose k equals n choose n minus k Pascal's recurrence, and the row sum, the sum over k of n choose k equals 2 to the power n.
Keep this key point in mind. The quantity n choose k is exactly the weight that the Bernstein construction attaches to the sample at k over, and this is no coincidence. It is the key to the entire construction.
The binomial theorem expands a plus b, all to the power n, as a sum of terms n choose k times a to the power k times b to the power n minus k. Now perform the substitution that drives the entire theory. Set a equal to x and b equal to 1 minus x. Since x plus 1 minus x equals 1, the left side is just 1, and the right side becomes a sum of terms n choose k times x to the power k times 1 minus x to the power n minus k. Those terms are the Bernstein basis polynomials. So for free, we learn that the Bernstein basis sums to 1 at every x. That is the partition of unity property. A quick linear algebra reminder. Polynomials of degree at most n form a vector space of dimension n plus 1. The obvious basis is the monomials 1, x, x squared, and so on. But on the interval from 0 to 1, that basis is numerically ill-conditioned. The Bernstein polynomials are simply a different basis of the same space. And that basis is non-negative, and it forms a partition of unity, which gives it far better numerical and geometric behavior. Choosing the right coordinates is the whole art. We measure error in the uniform norm, also called the sup norm, the maximum absolute value over the interval.
2 facts about continuous functions on a closed, bounded interval will be decisive. First, they are bounded. Second, by the Hein-Cantor theorem, they are uniformly continuous. That means, given a tolerance epsilon, there is a single delta, the same everywhere, so that inputs within delta give outputs within epsilon. That uniformity is precisely what makes Bernstein's proof work. Finally, the mode of convergence. Pointwise convergence means that, for each fixed x, the values converge. Uniform convergence is stronger. One error bound works simultaneously for all x.
Geometrically, as shown in the figure, the graph of the approximation p sub n eventually lives entirely inside a thin tube of width epsilon around the graph of f. When we say Bernstein polynomials converge, we mean it in this strong, uniform sense.
Here is the central definition. The kth Bernstein basis polynomial of degree n, written b sub n comma k of x, equals n choose k times x to the power k times 1 minus x to the power n minus k. Read every symbol. X between 0 and 1 is the variable. Think of it as a probability of success. K between 0 and n is the index. N is the degree. And n choose k is the multiplicity. In fact, this is exactly the probability of getting k heads in n tosses of a coin with bias x, the binomial distribution. Hold on to that probabilistic reading. It explains everything that follows. Each basis polynomial is a smooth bump. Its peak sits at x equals k over n, the sample location it is responsible for. As the degree grows, the bumps become narrower. So, near a query point x, the dominant weight comes from samples k over n that are very close to x, the Bernstein basis, therefore acts like a smooth, soft selector. The picture on the right shows the 5 bumps for n equal to 5. Notice how the peaks march evenly across the interval.
Two properties make the basis special. First, non-negativity. Each basis polynomial is a product of non-negative factors, so it is at least 0 on the interval. Second, partition of unity. They sum to exactly 1 at every point by the binomial theorem. Together, these say that the values b sub n comma k of x are genuine weights, a probability distribution. So any Bernstein combination is a weighted average of the data, and a weighted average can never overshoot the data. That single observation is the source of all the good behavior we will see. Now the boundary behavior. At x equals 0, only b sub n comma 0 is non-zero, and it equals 1. At x equals 1, only b sub n comma n survives. So only the end basis functions are active at the endpoints. This is why, later, Bézier curves pass exactly through their first and last control points. There is also a clean reflection symmetry. Replacing x by 1 minus x swaps the index k with n minus k, and each basis polynomial has a single maximum, located at x equals k over n. Compare degrees 3 and 8 side by side. As n increases, we get more bumps, each one narrower, with peaks evenly spaced at k over n. And crucially, at every x, they still add up to 1. This is the visual signature of the partition of unity, and it is what lets higher degree Bernstein approximations resolve finer features of a function. Now we build the approximation. The Bernstein operator of degree n applied to f, written b sub n of f at x, is the sum over k from 0 to n of f of k over n, the sampled value, times the basis weight b sub n comma k of x.
In words, b sub n of f at x is a weighted average of the samples f of k over n, with weights that concentrate near the grid points closest to x.
3 steps. First, sample. Evaluate f on the uniform grid, giving the coefficients f of k over n. Second, weight. At a query point x, attach to each sample the non-negative weight b sub n comma k of x. Third, average. Sum them. Because the weights sum to 1, the result is a convex combination of the samples.
One common misconception to flag now. The Bernstein operator does not interpolate f at the interior nodes. It only approximates. It does, however, match f exactly at the two endpoints. Here is the elegant reformulation. Let s sub n be a binomial random variable. With parameters n and x, then the probability that s sub n equals k is exactly b sub n comma k of x, and so b sub n of f at x is precisely the expected value of f of s sub n over n. The sample mean, s sub n over n, has mean x, and variance x times 1 minus x divided by n. As n grows, the variance vanishes, so s sub n over n concentrates at x by continuity. F of s sub n over n is close to f of x, therefore its expectation, which is b sub n of f at x, converges to f of x. This is the heart of Bernstein's proof, the weak law of large numbers plus uniform continuity.
Let us make the mechanism concrete. As n increases, the grid of samples gets denser and the binomial weights concentrate because the variance, x times 1 minus x over n, shrinks. So the weighted average effectively only sees samples whose grid point is very close to x, and those samples carry values close to f of x. The bar chart on the right shows the weights at x equal to 1/2, for n equal to 4 and n equal to 10. The distribution visibly tightens around the center.
Before the theorem, the intuition. Sampling more densely, while averaging more locally, lets us recover F2 effects compete, and both are controlled. Averaging introduces bias. It blurs F, but the averaging window shrinks like 1 over the square root of n, and the samples scatter around x, but with variance that tends to 0. Here is the honest caveat, which we will soon quantify. Bernstein convergence is slow, of order 1 over n for smooth functions. But it is universal and shape-preserving. That trade-off is exactly what makes it special.
Now the theorem, due to Bernstein in 1912. For every continuous function f on the interval from 0 to 1, the Bernstein polynomials converge to f uniformly. The subnorm of the error tends to 0.
There is also a sharp quantitative form, in terms of the modulus of continuity, omega. The modulus of continuity, omega of f and delta, is the largest change in f over inputs no more than delta apart. The error is at most 3/2 times omega of f at 1 over the square root of n as a consequence. If f is twice continuously differentiable, the error is of order 1 over n.
Step back to see what we have achieved. Weierstrass proved that polynomials are dense in the continuous functions under the subnorm. That is an existent statement. Bernstein's polynomials are an explicit, constructive witness to that theorem. To get within epsilon, just take n large enough. No abstract argument is needed, and a simple change of variable transfers everything from the interval 0 to 1 to any interval a to b. The proof rests on 3 exact computations, the moment identities. First, the basis sums to 1, partition of unity. Second, the weighted average of the grid points k over n equals x. The estimator is unbiased. Third, the weighted average of the squared deviations, k over n minus x, all squared, equals x times 1 minus x, divided by n, small variance. That third identity is the engine of the proof. The typical squared distance of a sample from x is at most 1 over 4n, which goes to 0. Now the assembly. Fix epsilon. By uniform continuity, choose delta so that close inputs give close outputs, and let m be the subnorm of f using partition of unity. The error is at most the weighted sum of the absolute differences, f of k over n, minus f of x. Split the indices into 2 groups, near, where k over n is within delta of x, and far, the rest. The near part contributes at most epsilon. For the far part, recall Chebyshev's inequality. The probability that a random variable lands at least t away from its mean is at most the variance, divided by t squared.
Applying that with the variance identity bounds the far part by 2m divided by 4n delta squared, which tends to 0 uniformly in x take n large, and the total is below 2 epsilon. That completes the proof. Take your time on the near and far split. It is the intellectual core of the argument. Our first example is computable in closed form. Sampling f of k over n equals k over n squared, and using the moment identities, the Bernstein approximation of x squared is exactly x squared, plus x times 1 minus x, divided by n. So it reproduces x squared, plus a transparent error term. That error is largest at x equal to 1/2, where it equals 1 over 4n, and it vanishes like 1 over n, confirming the general smooth rate. Note the lesson. Even a humble degree 2 polynomial is not reproduced exactly, but the bias is explicit and controlled. Here is the same statement in a picture. The true parabola in blue and the Bernstein approximations for n equal to 2, 4, and 10. Each approximation lies slightly below the parabola, and the gap is exactly that downward bump, x times 1 minus x over n, which shrinks as n grows. By n equal to 10, the curves are already very close. For the sine bump, the function f of x equals sine of pi x, watch 2 things. First, the approximations stay below the concave peak. That is a manifestation of shape preservation, which we will formalize later. Bernstein approximation preserves concavity. Second, the convergence is steady, and monotone in n each higher degree pushes the curve up, toward the true peak. The exponential, f of x equals e to the x, is convex, and that has a clean consequence. The Bernstein approximation lies above the curve everywhere. This is exactly Jensen's inequality at work. Since the operator is an expectation, and it preserves the mean, the expected value of a convex function is at least the function of the mean. So b sub n of f is greater than or equal to f, it is the convex counterpart of the concave behavior we just saw. Already at n equal to 10, the approximation tracks e to the x closely across the interval. Our fourth example, f of x equals the absolute value of x minus 1/2, has a corner at x equal to 1/2, and it teaches the limitation clearly. The Bernstein approximations are smooth, so they round off the corner, and convergence there is slow, order 1 over the square root of n rather than 1 over n even at n equal to 60, the tip is visibly rounded. The lesson, smoothness of the target controls the speed of convergence, not the fact of it. We still converge, just more slowly.
This slide overlays the same non-smooth example to dramatize the march toward the corner. Each increase in n pulls the smooth approximant closer to the sharp feature, but, as you can see, ever more slowly. It is a good visual intuition for the phrase, universal but slow. Now we quantify speed directly. On a logarithmic vertical scale, we plot the maximum error against the degree for 3 targets, e to the x and sine of pi x, which are smooth, and the corner function. The two smooth curves decay like a constant over, and the corner decays like a constant over the square root of n, and on this log plot, its line is visibly shallower. This single picture captures the role of smoothness in the convergence rate. Finally, for visualizations, here are all 13 basis bumps for n equal to 12, colored as a gradient. Notice the even spacing of the peaks at k over n, the smooth tiling of the interval, and the recurring theme that together they form a partition of unity at every x. This is the family of weights that the Bernstein operator uses. Now the payoff for geometry. Given control points p0 through pn, in the plane, the Bézier curve is the sum over k of pk times b sub n comma k of t. This is exactly the Bernstein operator, except the samples are now points, rather than numbers.
Because the weights are non-negative, and sum to 1, the curve is a moving weighted average of the control points. That is why dragging a control point moves the curve intuitively, and why designers love this form.
4 properties make Bézier curves trustworthy. Endpoint interpolation. The curve starts at p0 and ends at pn. Recall the endpoint behavior of the basis. The end tangents point along the first and last control edges. The convex hull property. The whole curve lies inside the convex hull of the control polygon, again because the weights are a probability distribution. And a fine invariance, transforming the control points transforms the curve. The figure shows a cubic curve hugging its shaded control hull. How do we evaluate a Bézier curve stably? The de Castelnau algorithm, which is purely geometric. Start from the control points, repeatedly take linear interpolations 1 minus t times pi plus t times pi plus 1, and after n rounds a single point remains, the curve value. The figure shows the nested midpoint interpolations for t equal to 1/2. It is mathematically equivalent to nested, Horner-style evaluation of the Bernstein form, and it avoids computing binomial coefficients explicitly, which is why it is the method of choice in practice.
Where do these run the world? In vector graphics. The path commands of SVG, PDF, and PostScript. In outline fonts, TrueType uses quadratic Bézier curves, while PostScript and OpenType use cubic ones. In computer-aided design surfaces for cars, aircraft, and consumer products. In animation, easing curves. And in robot and CNC toolpath planning. The reason is always the same bundle of Bernstein properties: intuitive control, guaranteed convex hull containment, exact endpoints and tangents, stable evaluation, and easy subdivision. Bernstein's 1912 tool is now the everyday geometry engine of digital design.
Let us collect the operator's algebraic properties. It is linear in F, it is positive and monotone. Non-negative inputs give non-negative outputs, and it preserves the order between functions. And it reproduces low-degree polynomials exactly. B sub n of the constant 1 equals 1, and B sub n of x equals x constants and affine functions pass through unchanged. This last fact connects to Korevkin's theorem. A positive linear operator that handles 1, x, and x squared well must converge on all continuous functions, which is exactly Bernstein's situation. The most prized properties are about shape. If f is increasing, so is its Bernstein approximation. If f is convex, so is the approximation and it lies above f. The approximation always stays between the minimum and the maximum of f. No spurious oscillation, no overshoot. And it is variation diminishing. It crosses any line no more often than f does. The figure recalls the convex exponential with its approximation sitting above. Shape preservation is rare among approximation schemes, and it is the main reason these methods are trusted in design. Let us be balanced. The advantages. The method is universal, working for any continuous f. It is constructive and simple to implement. It is non-negative, shape-preserving, and free of overshoot. It evaluates stably via de Casteljoux, and it carries beautiful geometric meaning. The limitations. It is slow, with error only of order 1 over n, even for smooth functions. It does not interpolate interior data. High degree is needed for high accuracy, and it is not the tool when you need spectral accuracy. Choose Bernstein and Bézier when robustness and shape matter more than raw speed. This table places Bernstein among its peers. Bernstein converges slowly, but it is shape-preserving and extremely robust. Equispaced interpolation can actually diverge, the Runge phenomenon. Chebyshev interpolation achieves spectral accuracy on smooth functions but does not preserve shape. Splines give algebraic rates and partial shape control. The takeaway: there is no free lunch. Bernstein trades speed for guaranteed good behavior. For high accuracy on smooth data, Chebyshev wins. For safe, shape-faithful design, Bernstein and Bézier win.
A consolidated map of applications. In approximation theory, constructive density and Korevkin-type theorems. In graphics and computer-aided design, Bézier, B-spline, and NURBS modeling. In image processing, smoothing, morphing, and vectorization. In animation, easing and motion paths. In numerics, Bernstein bases for isogeometric finite elements. In probability and statistics, binomial moments and Bernstein density estimators. In optimization, certificates of positivity on the unit interval. And in machine learning, monotone and convex regression and neural approximation theory. The unifying thread is that non-negative weights, summing to 1, make the methods both interpretable and safe.
Let us gather the essentials. The basis, b sub n comma k of x equals n choose k times x to the power k times 1 minus x to the power n minus k, non-negative and a partition of unity. The operator b sub n of f at x is a weighted average of the samples f of k over n.
It converges uniformly to f, a constructive Weierstrass theorem, at rate 1 over n, for smooth f. The clean identity, b sub n of x squared equals x squared plus x times 1 minus x over n, summarizes its behavior. And geometrically, the same formula is the Bézier curve, convex hull, and shape-preserving. In one sentence, sample, weight by binomial probabilities average.
4 takeaways to leave with. First, a single construction bridges probability, approximation theory, and geometric design. Second, shape preservation, that is positivity, monotonicity, and convexity, is the property practitioners value most. Third, the Bernstein, Bézier form is the computational backbone of computer-aided design, fonts, vector graphics, and animation. And fourth, always remember the 1 over n trade-off, robustness over speed. If you remember one thing, let it be this. Bernstein polynomials turn samples of a function into a safe, convergent, geometrically meaningful polynomial.
Now references split across 2 slides. For the approximation theory, Bernstein's original 1912 paper is the primary source. Lawrence's monograph, Bernstein Polynomials, is the classic reference. And DeVore and Lawrence, together with Cheney, are standard approximation theory texts. For the geometric design side, Farin and Protzsch, Bohum and Palesny are the standard references for computer-aided geometric design and the Bézier connection. The biographical material follows the Wikipedia article on Sergei Bernstein.
That brings us to the end. We saw how a probabilistic idea, averaging samples with binomial weights, yields a constructive proof of a deep theorem, and at the same time, the geometry that underlies modern digital design. Thank you for your attention. I'm happy to take questions.